Yeah.
Ok, eso mañana lo pongan en la página del ayuntamiento de
Pero
Bardají.
es que está...
Lo proyectan aquí en la
Te quería sentar ahí.
Ah, no te preocupes, pongo ahí porque sí tengo, si alguien se conecta o escribe por este lo veo.
Nos falta un estudiante.
Ya. Pero no sé si no.
¿Que nos falta?
Una ponente.
Voy a por ella.
¿Sabe que tenga presentación?
Supongo. Doy fe que ha ensayado.
Estaba ahora terminando de enseñar.
Toma, un griego.
Mucho bueno. El greco.
¿En español cómo se llama? El greco.
El greco.
Porque está anterior.
No sé, yo tenía pensado que...
Te has cortado el pelo. Raúl, te has cortado el pelo.
Faltaba yo.
Ahí está.
No, pero bueno, es bueno. Lo pongo yo.
Okay.
Shall we start? Yes. So thank you for being here. And today we have the presentations from the summer fellows that have been with us for 2 months. And sadly, they are leaving after this. But I hope you enjoy the Clàudia is going to start with a presentation about multi-wavelength properties of classical Novae. So, you want? Sorry.
Hi, I'm Clàudia, and I'm going to talk about the project I carried out this 2 months in CEFCA, and it is a multi-wavelength study of classical Novae. First, I must introduce what is a classical Novae. Well, it is a thermonuclear runaway that happens in the surface of a white dwarf, and this white dwarf is in an interacting binary system with a companion star. What's happening is that the companion star is transferring mass to the white dwarf, and as a consequence of this, sometimes you can see an accretion disk that is formed due to this. But what triggers explosion is that the material that is being transferred is accumulated in a layer on the surface of the white dwarf, and at some point the pressure is enough to start nuclear warming. And after this, it triggers this explosion, and the material is ejected into this interstellar medium. We must highlight that the binary system is not destroyed after this. A proof to see this explosion is to look at the light curve of the nova, and we observe that there is a rising in the magnitude of 8 to 12 magnitudes, and the beta rise at a big magnitude. This happens in the time of a few days, and later it starts to progressively decline in a week, in a time of weeks or months, and then it arrives again to the quiescence state. To characterize this, we use what's called the decline time, which is the time it takes to decline any magnitudes from the peak magnitude. The most commonly used are T2 and T3, which are the time it takes to decrease 2 and 3 magnitudes, respectively. And another feature we can see in the light curve is that some of the novae show this dip in the light curve, which this means that they have formed dust during the process. Another way of having information about novae is looking at the other parts of the spectrum. And here there's a schematic timeline of the physical processes and the electromagnetic emissions due to this. And here we can see that there is some X-rays, the X-rays due to the explosion, some gamma rays. Here is the peak of the ultraviolet and optical, and also the vision in the infrared says that there is dust and other things in X-ray and radio. But this is what they know about what happens in the moment of the explosion, and later what happens months to years later. But we don't know exactly what happens after this. So let's see what's happened. To study this, we use the input catalog that was used in the paper from Sarah collaborators, that is formed of 465 Novae, and we improve this by using some of the coordinates that are in the papers from Tapper and collaborators. And to begin this study, we start with the optical. We use the Gaia DL3 data. We did a cross match between our catalog and Gaia, and we found that we have 349 counterparts. And additionally to this, we also computed the Gaia spectra and the synthetic photometry of J plus and J plus. But, well, having Gaia's data led us to work with Novae that have a very accurate distance. And for this, we did a parallax correction, which is that the relative error of the Novaes had to be less than the 20%, which leaves us only with 64 Novae to work. And, well, there's another issue, which is the extinction, and it has to be corrected also. The extinction is the phenomenon in which there is interstellar dust between the satellite and the sources and makes the sources look fainter and redder. To correct this, we used to use a dust map that we applied first in the optical, and then it was applied in the infrared and the ultraviolet. But doing this, we also found another issue, that is that this map is unreliable at low galactic latitude, so we had to apply another curve that deleted more sources. To see the result, we used a color magnitude diagram, and in which we colored the nova with the year of discovery, which is the time that the explosion was recovered. And the result is that we lost 17 nova, and we are left only with 39 in our final plot. But well, let's see what this plot is telling us. First, we don't see any correlation with the age of the nova, but we see that our nova are in the same region that are the novas that are classified with having a high mass transfer rate in the paper from Abril and collaborators. This means that they will have set dominated by an accretion disk, and also we know that this nova with this feature peak in the ultraviolet. So let's see this range of the spectrum and what tells us. To do this, we use the GALEX survey, but we found another issue, that is that GALEX avoids the galactic plane, which is where the majority of the Novae are, and we only have data for 21 sources. So we wanted to check which is the relation between the year of discovery and the color. First, we can see that maybe the younger a nova is, the redder it is, but there is no correlation in the end. And also we try to see if there is correlation with the normal, the ultraviolet color, and we also don't find any correlation. Which in reality we expected this, but it is a little bit disappointing. So let's move on to the infrared spectrum and see if we find something else. To see in the infrared, we use the surveys of 2MASS, WISE, and SPX. And having infrared data finally let us construct a complete set of each nova. That is what is shown here. And our novas are also colored with the year discovery, in which we didn't see any pattern neither. But we can infer some things from this plot. First, we see that some of them follow this power law, and this means that they form an accretion disk. And also from the novas that we know that they are not following this behavior, we know that they are not formed an accretion disk or not completely formed. So later we can also infer that some of them show this one in the near infrared, meaning that we could be seeing the contribution of the companion star. And finally, we can also see that some of them have a little rise in their far infrared, meaning that they could have formed dust. So continuing with the infrared study, we decided to see if there is a correlation with P2, but we don't see any correlation either. But we thought, okay, let's do a histogram of this data, and we found this. They have abnormal behavior, which is what we expected because it completely confirms what is in the paper from Chong and collaborators, that this percentage is the same as it is shown here, and are the ones that produce dust. And relating to this, we decided to plot the set of individual nova that are classified as having a dust dip in their light curve. We see that their set are very similar, but what's more important is that they show these bumps, these risings in the far infrared, which confirms completely that this is the emission of cool dust. And well, to conclude my presentation, the main key points are that we found that the sources with an accurate distance are the ones that are in the high mass transfer rate, that there is no correlation between the studied electromagnetic signatures and the year of discovery of the nova, neither with the T2. The infrared signatures lead us to distinguish between the population that have an accretion disk and dust production. And finally, we confirm that the ones that are classified having a dust dip are also the ones that show the dust production feature in the spectrum. And to the future, we will continue the work writing a paper with more findings, in which we will include the study of the spatial distribution of the Novae within the Milky Way, and also we will use an alternative dust model. Sorry.
So this is post-explosion and post, this isn't quiescence, right? Post-decay.
Sorry.
So it's just the time it takes them to reform the accretion disk, I guess. When you say they don't have an accretion disk, right? Is that they haven't reformed it because it gets disrupted by the eruption?
No,
Or they don't have it to begin with?
They don't have it to begin.
it's a little bit beyond the scope, but I think that it is not destroyed.
Yeah, it's not. No, in this case, the disk is reformed within the first couple of weeks. So
Are they magnetic? Or what?
and so the ones that you see that that they may not have a disk is because they're magnetic or partially magnetic. But there was DQL among them.
Yeah. Well, we know who we
Yeah.
Questions?
Is there any known correlation between the T2 and any property of the Novae?
What we studied, there is no correlation with the colors and T2. Nothing.
Questions? I have one. The fact that you don't see the accretion disk means that they are not high transfer rate mobile, or not necessarily?
I think so. Less low. The rate is lower.
God knows.
So why they were in that part of the diagram? So normally systems with the accretion disk are in that part of the diagram because the disk is hot and they move to the hotter side of the diagram, right? So if they are there and they may or may not have the disk, what makes them hotter?
That's the God knows part of the answer.
Okay. Any other question?
Actually, if they don't have any accretion disk, does it mean that the material is falling directly into the star without orbiting first? Or, I mean, is the nova like more instant, or how does it work?
In that case, we're speaking about magnetic systems. So the disk is destroyed by the magnetic field. So the accretion goes through the magnetic field, follows the magnetic field lines.
Sorry, I understand magnetic. No.
No, yeah, yeah. It's okay. So I don't know either.
Yes, any other question? No? Next one in the queue.
Esa que estás diciendo yo.
De tantas ganas.
No he dicho Ani.
Y la serie de información.
Vale, vamos.
Okay. Next one is Carolina, who's going to talk us about exploring the activity cycle of AGN jets.
Well, hi everyone. As Juan introduced me, I'm Carolina, and I'm going to talk about the activity of the cycle of agents. So most galaxies host a supermassive black hole in their center. And when this black hole is accreting matter, we say that it's an active galactic nucleus, or AGN, which emits in all wavelengths going from the X-ray to the radio. Most of this emission is non-thermal in the form of synchrotron emission, as we can see in the jets here. Agents were thought to be rare in the past, but now we know that they play a central role in galaxy evolution. This is because the observations have shown that, well, what we thought is a coevolution between the host galaxy and the AGN. And this this happens because of the AGN duty cycle. What is this? It's that the AGN returns energy in short periods, while it's followed by long dormant periods. So it's just a cycle of activity, then a sleepy AGN, to say so, and again. And this energy that is returned to the environment is what we call feedback, and it's what regulates both star formation and the gas supply of the galaxy. This feedback comes in two main modes, the radiative mode and the kinetic mode. The radiative mode dominates in more luminous AGN, which are a minority, and comes in the form of radiation and winds. And the kinetic mode, which is the one that we are interested in, dominates in low accretion AGNs, and it comes in the form of jets, which is translated in synchrotron emission in the radio wavelengths. Why is this mode important? Because as Ivan Maroni has shown in the work, the kinetic mode dominates the energy budget of the feedback of AGN at low ratios. So, this is shown. So the thing with this mode is that it has not been yet characterized, or at least not very well, because we didn't have the statistical and scale coverage needed to do so. But with wide area surveys that are being done at the moment, we can do this. So the goal in this project is to determine the ages of the jets, to try and in a future work relate the properties of the host galaxies with the AGN jets. So first we're going to start with the sources in the GHz catalog, which is a multi-wavelength catalog that combines optical, infrared, and low frequency data, radio data, from about 500,000 sources. And we're going to cross-match it with Bello, because it has 3 radio frequencies that we're going to need for the spectral aging. To do this, we're going to do a cross-match on the lots IDs, because they will share the lots, the lots identifiers, because they share the lots sources. And then with the remaining sources, we're going to do a positional cross-match with the optical coordinates. And then we're going to add the Lemon class-wise redshifts from D plus DR4, which are computed through a neural network called Lemonade, that they are like photometric redshifts that we get from stethoscopic redshifts from different surveys. So to see if this has been done correctly, we're going to compare the Lemonade class-wise redshifts with the combined GHz and Bell redshifts, which are the redshifts that were available in those catalogs. And as you can see, although the limits are a little bit different between them, they will follow a one-on-one relation. So we see that we have done this correctly, and this is what we expected to get. Then the next step was trying to see if we combine the lemon plus Y's and lots recipes, we got like more precise estimates. This is because lemon plus Y's has really precise estimates because they are based on narrow bands from J+, but lots, although it's not as precise as lemon plus Y's, it reaches fainter sources. So maybe we could have the best of both worlds with that combination. So how do we do this? We're going to follow Hernán Caballero method, which is basically conflating the PDFs. This means multiplying the probability distribution functions of the redshifts and normalizing them. This would be like the visual result that we get comparing the photometric redshift with the spectroscopic ones. And we cannot really see a difference here. We think that this is very similar. But if we go to the numbers, if we do a statistical comparison based on the relative error, the central values do not really get better when we combine them. The lemon plus Y's races are already very precise on their own. But if we compare the median error and the percentage of sources with an error below 0.05, we see that they improve. But this has to be taken with caution because both lemon plus Y's and lots rely partly on Y's. So this means that they're not fully independent, and this could lead to an underestimation of the errors. But because we are interested in the central values and these lemon plus Y races are the most precise of these three, we're going to take this for the rest of our work. So now we can go on to the main part of the project, which is determining the ages of the jets. So first, we have to introduce that we are going to determine the break frequency, which would be this frequency right here, of a broken power law fitting. So these are not fits, this is just some examples of how our alpha 1 or alpha 2, which are the two slopes of the broken power law, can look like. This, for example, would be a double negative slope, and this would have a break that is what we're really looking for. Alpha 1 would be the low frequency slope, and alpha 2 the high frequency slope. And this would be our sources, the sources that we would be introducing in the fitting. There are around 10,000, and it's divided in four quadrants. It's divided in 4 quadrants. Here you can see the spectral shape of the slopes, and you can see that most of the sources lie in the 3rd quadrant, which means that they have a double negative slope, but some of the sources are moving upwards and onto higher frequencies and more flatter slopes. So these would be the sources that we fit. And why do we do this fitting? Why do we want the break frequency? Because as the jet ages, the emission goes on to lower frequencies. So this means that the break frequency is kind of a proxy of the age. And we can get this by fitting, as I said, a broken power law, a smoothed broken power law. But we only have 3 data points and 4 parameters, the 2 alphas, the break frequency, and the flux related to the break frequency. How do we amend this degeneracy? Well, we are going to fix alpha 1 to 2 possible values that are extreme cases. The first one is 5 halves, which corresponds to this slope, that is basically the self-absorbed synchrotron slope, and a flatter slope equal to 0 for various various of these slopes like combined together, right? So this would be an ideal case, and this is like a more typical case. So now you can see some fit examples. This is for the first case of alpha 1, 5 halves. So this alpha would be fixed, and this would be for alpha 1 equal to 0. This is also fixed. These are the boundaries that I have set for alpha 2 and for the break frequencies. This would be an extrapolated part, and this is the part where we have our 3 data points, the break frequency, and we can see the break frequency in most cases lies between the lots and the first frequency, these 2 points. And most of the fittings behave as we expected. So this is a break frequency distribution that we got. As you can see, for the first case, they pile up next to the lots frequency value, which is around 0.1 GHz. And for the second case, you see a wider variety of break frequencies with a larger tail. But they both have this distribution. And then, how do we get from the break frequencies to the ages? Well, when I say ages, I mean like the cooling time of the jet particle distribution. This is what we are seeing. So this is related to the magnetic field, to the break frequencies, that's what we wanted, and the redshifts. So to obtain the magnetic field, we assume a equipartition, which means that the energy of the particles and the magnetic field are equal. So we get an equation that basically is related to the synodal luminosity, the volume of the sources, and other constants. Then this term is presented like an equivalent magnetic field, but it's like the inverse quantum electrons that are scattered for the photons of the CMB. And then the break frequencies and the luminary passwise redshifts. Okay, so this would be the age distribution that we get. They're both very similar between the two alphas. The main difference would be that the alpha one, the first case, has an older median. It's the jets are a little bit older, and there are more good fits in this case. But overall, we see that we got a really young jets. We can also study the size distribution. For the purpose of the calculations, we divided them into compact sources and extended sources. But as you can see, they're really compact because most of the sources have sizes below 40 kiloparsecs. So they're really compact in general. So just to sum everything up, we studied two extreme cases for alpha 1, and they both gave similar ages and sizes distributions. So the results don't really depend on this assumption. But if we had to choose one of them, I would go for alpha 1 equal to 0, because the alpha 1 equal to 5 halves gave break frequencies that were piled up next to the loss frequency, which could be an artifact of the fitting process, and also this is like the more a real case. The distributions gave us sources that were young and compact with ages below 40 megayears and sizes below, most of them, 40 kiloparsecs. So this is compatible with the AGN active phase duration typical, that is like below 100 megayears, and it's also compatible with the results of Vigo and Merloni, who found out that the energetic budget was dominated by young compact sources, which are the ones that we found here. And also it is consistent with short-lived jets because it's really young, so it shouldn't be, we shouldn't have jets that live for so long. So this is also consistent with the AEN duty cycle that I mentioned at the start. So, yeah, so thank you.
Thank you very much. Questions? No questions?
How many sources did you manage to get at the end? How many?
At the end, for the alpha 1, they were around 4,000, and for alpha, well, they are both alpha 1, but for the first case, around 4,000 sources, and for the second one, 3,000 or so. Yeah, so a little bit less than the half of the ones that we first had.
One thing that I probably missed, did you fit both prescriptions into all sources, or did you pre-select which ones you're going to fit with one?
So we started with like around 500,000 sources, but we could only fit the ones that have 3 frequencies, so that are like 10,000. And then from that, because we did put some boundaries there, we only could get the sources that I just mentioned. So it's just a small subset of the sources. And we did like 1 fit for the first alpha 1 value and another fit for the other one. So it's separate. Yes.
Again, maybe I missed it. What is the redshift range that you're covering?
Yes, so approximately between 0 and 4 because of the unveiled redshifts. It could be maybe around 5 also, but more or less it's, yeah, 4 or 5. Around that, yeah.
And you can go to the redshift figure.
Yes,
Right.
there. Yeah, more or less. You can get some sources that have a higher redshift, but most of them like in that range.
Most below 1.
Yes,
So you have radio data for the whole redshift range, which goes all the way to 4.
not for all the sources, but yes.
All right.
If you go back to the examples with the 5/2, yeah, like in this case, just by eye, right? I could easily see the A10 also fitting the data, right? So
Yes.
how do you decide in this case which ones you trust more? I mean, I don't know if it would necessarily give you a quite distinct break frequency, right?
I mean, what I did to decide and to stay with this option was because of the results more than for the fits. So you see that they build this result pass up next to the range, to the edge of the range, which is kind of weird, right?
Which is what you
it
would
could be-
expect when you
Yeah,
fit something
yeah, it's
like this.
this is also for this case, this is an ideal case. It's like the typical slope would be between these two, these things, right? So this would be like the upper value and the lower value maybe. So it should be like in between. There are two extreme cases. You cannot really trust any of those. You have to look in between them. So, but I would go for now for this case for that reason.
I guess if the loss frequency wasn't that, but a different one, the brace would pile up at that different frequency that you got, right?
I think so. Like it's piling up at the lower age, and it's consistent every time we did this. So, yeah. Any more questions? Yeah.
For the very nice results. So when you present the sizes, these
Yes.
are optical, these are radio sizes.
These are most of them. Well, the reason I will go to that, but the reason why we divided them was because we had to choose the semi-major axis between the deconvolved semi-major axis, which I think are optical. No, they are radio, and the third of the size of the beam. So this would give one option or the other. So in general, they are radio sizes in both. Yeah.
So with the age, you can have an idea of the velocity of the jet.
With the age.
Not the age of the jet, you have
I
the
will-
size, you can measure the velocity in which the, and if that makes sense with what you expect.
If the radiative age, so if the expansion took only in the last radiative active period, then they should be related. But if you had recurrent events, then the last event may be very young, but the size might be larger.
Okay.
And there's also the apparent luminal velocities. The apparent superluminal velocities of the jets. So if you don't know the inclination,
Yeah.
you will answer.
I did not study that, so I don't know. But yeah. Any more questions?
Can be.
I have to connect. Igual tengo batería, pero no sé.
Vamos a asegurarnos
Vale.
que luego nunca se sabe.
Ahí va, que lo spoileo.
Vaya a la conclusión directamente.
Uy, mis padres. El fin discreto. Sorry.
Eso no es nada.
Pues tengo no con las contraseñas, pues perdón. Ay. Madre mía. Bien.
La foto del gato como de pantalla.
No, ya he cerrado todo.
Si quieres usar el puntero, conecta el cacharrillo ese.
Bueno, yo creo que me apaño.
¿Sí? Vale.
Bueno, y le señalando.
Okay.
Okay, my name is Pilar Bello. I've been working at DPAD.
I was going to to end the session, we have Pilar Reyo, she said, we're going to talk about machine learning model to automatize the quality control in image redaction. Check yourself.
She's quick. My bad, sorry. Okay. So first of all, I'm going to explain why this project is necessary. In the image reduction process, there's a step in which we have to make a super background correction. But what's a super background? Okay, a super background is a common background of a set of images that has information that actually we don't want in the final image, like optical and electronic signal. So we have to do like this correction. But first of all, we have to generate the super background. So the super background is created with a set of images with pattern stability. And here we have an example of images that have been used to create a super background. This is the super background created, and this is every process. The image before super background correction, the super background used for the correction, and this image with the super background correction. Okay, here's another example of why the super background correction is needed, because this is the before the correction and after the correction. So, as I've said, to generate the super background, we need like a set of images. But there's one condition, and is that these images have to be free of any artifacts. So I brought to you some example of artifacts because these shouldn't belong to the super background. So, for example, here we see a gradient of a very bright star that maybe would be around here. Some reflections, these also are these reflections right here. So actually, this would be like images that would not be valid to create a super background. And for almost 3 years, the bad staff have been like manually flagging the images to say, okay, this one has an artifact on them, so we cannot use these images. But we want a machine learning model to automatize this selection. And I'm sorry because I'm a bit ill, so. So we're going to generate, a model that is going to select the right images or the images with the artifact to not use them to generate the super background. And we took advantage of the almost 500,000 images that have been already flagged by the bad staff. And we use it to train the model. So in the training phase, we are going to use render images with the next metadata. If the metadata has a level of 0, that means that the image has no artifact on it, so that image is valid. And if the level is 1, that means that the image has some artifact, so the image would not be valid. So we got our training model, and then we have to test the model. So we give the model like a set of images, and we ask the model to classify the images. But one important thing here is that the model is not going to take a binary decision for us. The model is going to give us like a continuous score between 0 and 1, meaning that values like 0 or close to 0, the model is quite sure that there's nothing on the image. But if we got values of 1 or around 1, but close to 1 actually, that means that the model is quite sure like there's something in that image. Okay.
I have to say that I'm not an expert on machine learning, so I'm going to try to give you just a brief overview of machine learning. Okay, when we train the model learns by changing its internal parameters, which is actually something that we cannot change, something that happens during the training. And the operation that is done to learn is a convolution. So for our concrete model, we got an architecture of 3 convolutional blocks. And one thing that is important, as the image goes through the model, the image gets like smaller in size, but deeper on channels, because at first we've got 3 channels, RGB, but it goes deeper and deeper and gains more channels, because more or less the channels is where is going to be the information that the model learns, like the filters that are going to detect the patterns of the artifacts. Wait. Okay, I've done a lot of experiments, a lot of changes, but I'm going to highlight just one key change because of the improvement that it brought to the model. I saw something in the results. I saw that this is the same artifact. I don't know if you can see the one that is below. Yes, okay. So the only difference between them was that this is more intense than this one. This one was not detected because it got a really low score, but this one was detected because the score is much higher. This shouldn't happen because the artifact is the same, so it should be detected. And I thought, okay, as I told you before, as the image goes through the model, it gets reduces. And I thought, okay, maybe this reduction was too aggressive because the reduction is done by doing the average. So maybe more local and weak patterns are like lost when doing the average. And I say, okay, maybe we can change it to a 4x4 image. And so that it was a good change because this local and weak information was more preserved when doing the average, so that these images that at first were not detected, now they are, because they got like higher scores. So I think it was one of the most important changes. Okay, I first started on my local PC with small experiments, just one filter, but then we wanted to try a more general model with 11 filters, but it took me almost 1 hour almost 1 week to be completed, which is way too much. Then we moved on to the HPC. So we divided the training process into several processes that we could parallelize. We had to make some changes so that the processes could communicate with each other. And right now, what it initially took me 1 week on the HPC, now it takes us 4 hours. So it's a major improvement. I have to admit that I used the whole HPC. So on August, the HPC has been all mine. Okay, and we have to check the model's performance. So basically, we based on two plots. The first of it is a histogram. And the first thing we see here is that there are 2 groups, the green one and the red one. The color is going to tell us like the real information of each image, like the real level of the image. But the histogram shows us the distribution of the scores that the model has given. So, of course, the more separated these two groups are, the better, because that means that the model knows how to separate and discriminate well between the 2 sets of images, valid and not valid. Of course, we are always going to have values on the middle, but as you can see, there are just few of them. Like there are 2 big groups in 0 and 1. Okay, but I have to make a selection of the images. I have to select, okay, I have to say, this is the images that I'm going to take to create the super background. And I do this by picking a concrete threshold. For example, if I pick a threshold of 0.5, that means that I'm going to select all the images that got a score of between 0 and 0.5. In this particular case, I would correctly select the green ones, but I would have like these red ones that be like leaked artifacts. So for each given score, we got a confusion matrix that is going to tell us like this information, how many images were correctly or incorrectly classified for each threshold. And this one is just for 0.5. We also wanted to see if, I'm sorry, my throat is hurting. We also wanted to see if it was better to have one specific model for each filter or a general model that could be used for all the filter, which of course is a more convenient solution. We test images from this filter because it's a very challenging one. And we test images of this filter with a filter specific model trained for just that filter and a more general model with 11 filters. And actually we got good news because as we can see, the more general model separates better between these two groups, like the discrimination is better. So it was just a small experiment, but this could suggest that as a more general model sees a wider variety of patterns, it can generalize better, but this is a small experiment. Okay, so the purpose of this project is to select the images to generate the super background. So we asked the model, the images, we asked the model to select the concrete images that the model would have picked to generate a super background. And we compared these super backgrounds generated with different thresholds with the original super background that had been already created by DPAD staff, by the selection of DPAD staff. Since the super backgrounds were like too similar between them, we analyzed it through the difference of the two super backgrounds, the original and the super background created with 0.3, 0.5, 0. As you can see, here's another example. As the threshold increases, you see like the two images are like more similar between each other. That's because as the threshold increases, I'm going to select more images, which is something good to have as images as possible. So I have less noise, I have the two super backgrounds more similar, but I'm going to take the risk of having more artifacts leaked. So that's a compromise decision that we have to analyze. So the purpose now is finding like the ideal threshold. So we analyze it through the next curves. The blue one is like the valid discarded that the valid images that would have been discarded depending on the threshold. That of course is going to go down because as I increase the threshold, I pick more images, so I discard less valid images. And the opposite happens with the leaked artifacts. As I go higher threshold, I'm going to incorrectly select more artifacts. And we plot this curve with several filters. Of course, this behavior is the same in all of them. We try to have an approach of what could be the best threshold by plotting this cross point between the two curves with the filter to see if it was some pattern here, but at first I think we saw nothing. I think there's no tendency or no correlation here. So finding like the ideal threshold is something that is yet to be explored. And we wanted to see if the decisions of the model were randomly taken or not. So we created these heat maps that are going to tell us at which part of the images the model is paying attention to say, okay, there's an artifact here. These are the examples of the artifacts I showed you at first. And as you can see, they are properly marked because you have like this, this region around here marked that corresponds to this gradient. The same with this. There's a gradient here that has been already properly marked. And the next examples are even more clear. Like these artifacts is marked, these two reflections of there are marked. So now we know the model is taking the right decisions, and not only that, but the model is also ignoring the things that we wanted to ignore, because the model, as you can see, is not paying attention to the stars. For example, it's not paying attention to these columns that are like the amplifiers of the filters, because we don't want the model to pay attention to these patterns, so the model is not paying attention to that. So here we have more examples. This reflection here is marked. The last one. And breaking news, because we didn't know we didn't know that if we were going to have enough time to train like the 56 filters, like the biggest training, but we did at the time to do it. And we got like a really good results because you can clearly see the two separated groups. So I think it's a really good news that I want to add in the last moment. And the conclusions are that I think that given the results, we achieved like really functional and reliable model that I think is ready to use. So the next steps would be like integrating this tool in the pipeline of image reduction, choosing the final threshold. As you can see, it's something that actually we didn't get to any conclusion. Getting advance of some improvements in the image reduction, like a non-linearity correction, that is going to make things easier for the model, because the non-linearity correction is like these patterns here are going to disappear. So it's even easier for the model to train, because the more patterns the images have, it's more difficult to the model, because it's going to look at these patterns, but they are going to disappear. So maybe that makes the model even better. I'm working on GPU, like trying to do the trainings on GPU, because so far all we have done is on CPU. And I hope you like it.
Pilar,
It's a machine learning.
questions? Varias?
If you go back to your comparison of the original super background versus yours.
Yes.
Of the other one, actually, I'm more interested in. Do you remember by chance the difference in numbers? How many images went into the original super background versus yours? Because I'm a bit surprised by the difference when your threshold is so low, which supposedly it's the really high confidence of good images.
Yes, but the amount of images is too low when you pick a low threshold.
The amount, sorry?
The amount of images is really low when you pick a low threshold. That's why maybe you have like too few images to generate the super background if you pick a really low threshold. Of course, the images are going to be like more probably to not have any artifacts, but the amount is going to be really low. I don't know, maybe I can show you through a histogram better. For example, if I pick a threshold of 0.5, I'm going to have all these right images selected, but the amount of images is going to be like too low, maybe, to generate a super background.
No, it's just, I don't know if I should be surprised that statistics make such a difference, but like this 0.3, that the fact that the fringing there is just so obvious between the two.
Yes.
Is, I don't know, like at first sight it surprises me, but yeah, okay, if one is 200 images and the other is 5.
Yes, maybe it's because of that, because the super background created with 0.5 threshold has like too few images. So the super background created is too different from the original super background. Like not enough images to learn the fringing.
And just, oh,
I may comment maybe. I think that in that regard, that maybe for the images with fringing, it is even more relevant to cover not only the images but the time of the feeling to get a good model of it. And maybe taking small threshold is not. It's not a good sample.
When we have fringing, sometimes we have to divide the line in two because it's not constant. The intensity of
so the intensity is not constant, but the pattern should be.
The pattern is constant, but the average of all the images does not correct properly in all the night. So sometimes you have to divide the night in several parts. So if you're comparing with the average super background with many images, a small selection of images might not be representative of the same So, yeah, so the average might not be exactly the same.
Oh, it's definitely an interesting exercise. And I do have a second one, if I may, on your last confusion matrix.
Of the whole training.
Yes.
Mm.
I am fairly certain that anyone looking at this matrix would be a bit disappointed, right? At face value, the 26, I don't understand your 26% there.
Yeah, this here.
Yeah,
That means if you pick a threshold of 0.5, like you transform of the scores from 0.5 to 1, just to a level of 1, so that the model would have predicted 1 and the real
Yeah.
level was 1. Like, and with a threshold.
yeah. No. I mean,
Okay.
I understand how a
Sorry.
confusion matrix works. I just, to
The
me,
thing
it
is
seems
that
like a
here,
very low number.
The total is 100%, right?
Yes.
So it's not the percentage of each block.
Oh, okay.
It's not the percentage of each block
It's
per
not,
block.
it's
Because
normalized.
normally they show this in, so this would be from 0 to 100. And this would be from 0 to 100.
Because
so
you know,
Okay,
from
no,
the-
yeah.
Getting a confusion matrix of 26, you'll be, oh, well, it's back
No,
to the drawing board.
Juan
Okay,
is right,
it's-
we
it's
decided to do
normal.
it like this, yes,
So, but how much is that? But still, it's 16 out of 60,000?
But if this thing means the threshold of 0.5 is still too low.
You need to separate in the denominator, you need to put the true value in this corner, not the total. So you know how well or bad you are performing in this block. Because otherwise you are comparing to the total. And you don't know.
Yes,
So this is much better than it looks. probably.
yes. Well, we decided to do it like this.
That's my fault. So, just to be clear.
It's all of it. It's a confusion matrix.
In the ideal case, you would have 100%,
Yes. Yes. Yes, for me it's clear because I'm used to looking at it like this.
Well, yeah,
But maybe
your work.
it's a confusion matrix.
I have a question.
Yes.
Can you use the heat map to weight the images when you combine them and you don't need to reject images?
To
Would that be
weight?
possible? This is a question for both.
I don't know. What do you mean by weight?
Because you know that that this is where the information is to reject the image. When you combine the images, you could put a weight here, a very low, so depending on the heat map. So this wouldn't contribute to the average, and this would contribute to the average. So you are
Okay.
not rejecting the information. You are using the heat map to weigh
Yes.
how they weight in the average.
I don't know, is that possible?
That is something that we are exploring, exploring
The thing is with the gradients,
for
if you
something
go to
very
the
specific cases.
Because this is a mask.
but go to the slide with only gradients.
It depends on the artifact. Some artifacts are difficult to do that.
So here you are not. In this one, you have a gradient in one corner and a gradient in the other corner, and the heat map is only detected discrete points.
So when you detect an artifact, it's something that affects the whole image. The whole image is
It
wrong.
could be
For
a
some reason,
image, could be a region, could be a reflection, could be a gradient.
I will try anyway because
Yeah, but those are worse for us, the gradients, and those are not perfectly weighted in the.
Okay.
So for instance, if is exploring in the particular case of the artifact being local reflection,
yeah, localized,
localized
quantified.
to that part to use the image. But otherwise, we just flag the image, and just to be clear, the actual image is not rejected from the data pieces, so it's not accounted for making the background, but then it is corrected and it's part of that.
And when you have the artifact, so when you don't have the artifact and you have the background, the gradient, this one, the machine learning detects those images, or you need something particularly strong to flag the image. So in these cases, the main artifact is here, but there are also some gradients there. No? So when this one is not here, that's the algorithm detects flags well these images, or you need something very.
I think so.
Yes, it's effective. I mean, these ones, I chosen examples of images that have been detected.
Yeah.
Yes, because it's what I explained with the change we made to preserve the more local and weak patterns. Maybe I should have brought one example of this, but you can do the heat map in any layer of the model. So in the last layer, we just uses like the image that has the most information, but it's reducing. So it's doing the average. And in the last layer, with image of just 4x4, you can see here, I have the examples that I didn't put there. Like all of this part is like resumed in one big mancha. So yes, when it's like when we the average, this thing is effective.
Okay.
I think your model is just see the where is the it shows the high contrast. For instance, for this amplifier, look just in the border where the contrast is high.
No,
actually,
I have to say that I don't know what the model is here.
This one, the model is doing this because in first slide, when you show the not detected, the reflection was same, but in one case was detected, in another one is not detected. If you back to
yes.
This slide, you see when the in detected
This
yes, in detected one, in the below one, because the background is black. If you explain in color, due to this is detected, but in top because the sky is brighter, is not detected. Your model is so sensitive to the contrast. If the contrast is high, it can be detected. If not, it would not.
Yes.
Detect. Yeah.
Yes.
And due to this, for that amplifier, just the more border is detected and in the heat map.
Okay, maybe that's the reason why, because I didn't know why this part was detected.
Yeah, when I saw this plot and compare with the heat map, I said maybe it has a high contrast, it's detecting the.
But mind you that then she fixes it. So actually the one above in the model is, so this is the old model.
Yeah, I know here is fixed, but in the later in the heat map we can see when it's the contiguous in the amplifier. It's
Yeah, and I know, but this is a better example because this one is fixed, right? So the one above
it was fixed. We should see in a heat map all the amplifier in red color.
No, we will.
If it's model here, if it's trained properly.
Can continue, but no, it is.
But it did miss it because of the reduced contrast. So this fix made it detected despite the lower contrast, but before it was missing it.
That's right.
Yeah. It is because of the contrast. But dividing the image in 4 regions makes it easier for the notable to detect them.
Questions? No? Next time. And the 3 of them for the model. Perfecto.
Tenía que pasar.
Esto es un recorded.
Caótica. Esa es una vez.
Right?
El resumen de la
Just still on the
mecánica
same.
viva.
It's still the same.
Falta un semestre.
Ay,